Alright, so this is the review for exam 3. We're going to start with number 1. So number 1 says identify the type of function, linear, quadratic, or rational, and then find a formula for each one. So this is obviously a rational function, and the reason for that is it has a vertical asymptote. So that's an easy one to identify. So function, a vertical asymptote obviously is right here at x equal x equal positive 3. So x equal 3. This is a linear function. And of course this one is a quadratic function. For the obvious reasons that this one is a line, and this one's an upside down sort of letter U, upside down parabola. All right, so now we want to find a formula for each one. So let's start over here with f of x with the rational function. Now a rational function has a polynomial divided by a polynomial. And remember, if you have a 0 on the bottom, you get this vertical asymptote. So if you have a vertical asymptote at x equal 3, that means you have to have an x minus 3 on the bottom. And that's the only vertical asymptote, so my guess is that there's nothing else down here, and it doesn't look like there's actually a root, so I would guess it's just a number on top, so I'm going to guess just 1. And if you graph this function, 1 divided by left parenthesis x minus 3, and we'll just do a standard window, so do 6. We'll see that, yep, we get basically what this function looks like right here. So that's a good guess for that function. Let's come back over here and look at the next one. Let's do this in a different color. So for a line, remember we have y equals mx plus b, so basically g of x equals some slope times x plus b, where b is the y-intercept. We can see the y-intercept here is the number 3, so we know this is going to be some number times x plus 3, and to figure out this number m, that's the slope. Well, the slope is the rise over the run. So you can see here, here's a rise, and here's a run. So there's a run of 5 and a rise of 3. So 3 over 5, and because it's going down, we'll put a negative sign in front of it. So it's negative 3/5 x plus 3. And again, you can check this on your calculator. So if you hit y equals, we can plug in negative 3 divided by 5 times x plus 3. And then just hit graph, and you'll see, yes, we get the same graph we have there. All right, let's look at the third one, which is a quadratic function. Notice this formula is given to us. So y equals some number a times x minus h quantity squared plus k. Remember, h comma k is the vertex. So we can use this information to find the formula. So here's the vertex of the parabola. So you go over 1 and up 3. That means our h is equal to 1, and our k is equal to 3. So down here, we can copy down the formula. H of x is equal to, we know the form, a times x minus h, quantity squared, plus k. And we can plug in. So we don't know what a is, so let's leave a alone. So then we have x minus 1, quantity squared, plus 3. And to figure out a, we need one more point. And so if you notice, they do give us another point right here. This is the point when you plug in 0, you get out 2. And so what we know is we can take this equation here, this is h of x, and we know the output is 2 when you plug in 0. So we're going to take 2 and set it equal to a times plug in 0 minus 1 quantity squared plus 3. And we can work this out. This is going to be 2 equal to a. Negative 1 quantity squared is just 1 plus 3. We'll subtract 3 from both sides, and this will give us a. So you get negative 1 is equal to a. So our final answer will be h of x equal to negative, instead of negative 1, we'll just put negative x minus 1 quantity squared plus k. Oh, plus not k, but 3. So plus 3 there. So that's the formula for that parabola. Now you can multiply that out and put it in standard form, but this is fine. This is a great answer. Let's check it on our calculator just to make sure we didn't make any silly mistakes. So we'll clear this. We'll put a negative sign, left parenthesis, x minus 1, raised to the 2, hit over, then plus 3, hit the graph button, and hopefully it looks just like we have there, and it does, so we know we did it right. All right, let's look at the next problem. So here they give us 3 formulas. I have f of x, g of x, and h of x. And again, we want to identify what type of function it is. Is it quadratic? Is it linear, quadratic, or rational? And so you can see this one, of course, is linear. This one, of course, is the quadratic because it has degree 2. And then this one is the leftover one, but it's obviously rational because you're dividing, and you have polynomial on top and polynomial on bottom. Right, so you should be able to recognize a linear, quadratic, rational, or even a polynomial function by their graphs or their formulas. And then we're going to answer these following questions, basically. So find the domain, the range, the X-intercepts, the Y-intercepts, the vertical asymptote, the horizontal asymptotes, and then finally graph this thing. So let's start with the hardest of the 3, the rational function. And we'll start here by simply finding the domain. And if you want, you can graph this on your calculator to kind of have something to help you as you kind of go here. So we can graph this, and we have 3x raised to the 2 divided by left parenthesis x raised to the 2 minus 5x minus 24. All right, so remember, you can use your calculator to help you, but you can't use it to solve the problem. But we can kind of look at the graph. You can kind of see there's a vertical asymptote there, and then the one there, it looks like. You can't see it over here, but there should be something coming down. It's probably not zoomed in. It's zoomed too close in, but it's just coming down like that. So what can we do here to find the domain? All right, so to find the domain, these are our input values. So to find our input values, you can see there's a vertical asymptote here, and there's going to be one right here too. So you can get rid of 2 input values, and that's when the denominator is 0. All right, so we have to find out when this denominator is equal to 0. So remember, there's 3 things that limit our domain. So 1, you can't have zeros in the denominator. 2, if it's a square root, make sure it's bigger than or equal to 0 inside there. And the third one we haven't talked about yet, but it involves ln functions, which we'll talk about in the next exam. It has to be bigger than 0. So right now, we're not even dealing with roots because we're dealing with polynomials or rational functions, which is a polynomial divided by a polynomial. So this is the only thing that can come up. This is the only thing that can limit our domain. So we're going to make sure that x squared minus 5x minus 24 is not equal to 0, so we should be able to factor this, x plus or minus something, x plus or minus something, not equal to 0. And so 24, 8 and 3 would work, or 6 and 4. But 8 and 3 is the right one because you can take an 8 and 3 and turn it into a 5 by subtracting 8 and adding 3. And so you want to make sure that x minus 8 is not equal to 0, and x plus 3 is not equal to 0. And so you add 8 to both sides, so x can't be 8, and x can't be equal to, here you subtract 3 from both sides, so negative 3. So on my number line, what do I have? So at negative 3 and 8, I'm going to have these big holes. So I'm going to have a hole here and a hole here, but everything else is good. So I'll shade in everything else. So this is all in part of my domain, so I write down d equals, at an interval notation, negative infinity to negative 3, in parenthesis, union, parenthesis, negative 3 to 8, in parenthesis, union, 8 to infinity. Okay, so that's my domain. Now the range is a lot harder to figure out, so let's take a look at this graph. So the graph of this thing I don't actually, I need to zoom out a little bit more to kind of see what's happening here. So let's take my window and let's zoom fit it first and see what that does, because that's going to fit that output to the input. And you can kind of see it over here now. The problem is that these numbers are just way too big. So if you go down here, you can change these a little bit. So maybe make it -50 to +50. You may get a better picture. So I just could adjust them by looking at them to see what happens. And so now I can kind of see, yeah, this is coming down. All right, so for my range, I probably wouldn't ask you this question on an exam because I think it's a little tricky. You really need to look at the graph and need to have a good picture of the graph, which is hard to see here. But you can see that how it comes down, and it comes down here. If you go back to your standard window, it looks, now you can kind of read it off a little bit better. The problem with this one is that right here it looks like there's a gap. You see how it goes to 0 and there's a gap here? So if I was going to write down my range, all right, so for my range, I certainly would have -infinity to 0. And I would include 0 because you can see if you plug in 0, you're going to get out 0 because you have 0 on top and -24 on the bottom. But it's hard to see that there's actually a gap here, and there is a gap. There's a gap probably all the way up to the number 3. Right? There's a horizontal asymptote at 3. So again, this would be too difficult for an exam because the picture's not nice enough. So it would be union 3 to infinity, and that would be my range. And again, the reason for that is if you think about it, here the outputs go up until 0, and there's kind of a jump all the way up to 3. Right, this thing comes down and then starts to level off right here, heading towards height 3 as you go out to the left. The same thing happens on the right. It comes down, and I'll start heading off to height 3 on the right. All right, so this would be my answer right here. Okay, so that's my domain, that's my range. I need X-intercepts and Y-intercepts. So let's do those right here. So for an X-intercept, and then a Y-intercept. Now these are always a little bit tricky, and to figure out which one is which, I always like to draw a picture because I know what an X-intercept actually is. So here's my X-axis and here's my Y. You can label this X and Y if you like. And then you want to remember an X-intercept happens on the X-axis. And so what identifies that point is you don't know how far over you're going to go, or whether you're going to go right or left, but you do know the height is 0. So this one, the output is equal to 0. So you're going to take 0, and you're going to set it equal to your original function. So 3x squared, all divided by, and then you have x squared minus 5x minus 24 on the bottom. And you're going to solve this. So now remember, when you solve, you're going to first clear denominators, which is very easy. You just multiply both sides by x squared minus 5x minus 24. On the left-hand side, you'll still get 0 because 0 times anything is 0. But on the right-hand side, you're going to get this 3x squared. You're going to divide out the 3. So you divide both sides by 3. And you get 0 equal to x squared. And of course, take the square root of both sides, and you just get 0 equal to x. So there's one X-intercept at 0, 0. And then for the Y-intercept, so now remember this one, you have X and you have Y. And this is where you cross the Y-axis. So I don't know if it's way up here or way down there, but I know it's on the Y-axis. So I know the input is 0, whereas the output, I don't know. Right, so this basically says plug in 0 into the function. So f of 0, which equals, you're going to get 3 times 0 squared on top. And then you can plug it in the bottom. So 0 squared minus 5 times 0 minus 24. And so you get 0 on top and -24 on the bottom, which is equal to 0. So here, if the input's 0, the output's 0, so you get the point 0, 0. So it's X-intercept and Y-intercept are exactly the same. Right, so now we want to find vertical asymptotes and horizontal asymptotes, and then conclude with the graph. So for vertical asymptotes, this is when the function blows up or blows down. So remember the function was this 3x squared over x squared minus 5x minus 24. So that's when the bottom is equal to 0. That's how you get a rational function to blow up or blow down. The denominator winds up being 0, and you have some sort of number on top that's not 0. So you either get a big number out or a really big negative number out. So find out when this is equal to 0, and we're going to get those vertical asymptotes, which you can see on here. Here's the vertical asymptote here. There's one, and there's another one. So we should have 2. Okay, so we're going to factor this again, which we've already done. So it's just x minus 8 times x plus 3. And for a different reason now, we're setting it equal to 0. Before we were setting it equal to 0, and it was really not equal to 0 because it's finding the points that were not in domain. Now we're finding when it blows up and blows down, so we're setting it equal to 0. And so we get x minus 8 equal to 0, or we have x plus 3 equal to 0. And you move over the 8, so x equal 8 is one vertical asymptote, and then you move over the 3, so you subtract 3 from both sides, and so x equal negative 3 is the second vertical asymptote. For the horizontal asymptotes, let's write this function down so you can see it here. So f of x, remember, is equal to 3x squared over x squared minus 5x minus 24. So for horizontal asymptotes, either you want to look to the right or to the left. Now for rational functions, you can just look to the right. So as x goes to infinity, where does f of x go to? And what you want to pay attention to here are these degrees. So this has degree 2, this has degree 2. So since the degrees are exactly the same, what's going to happen is it's going to go to 3, and there's a 1 here we don't write, over 1. So 3 divided by 1, which equals 3. So with rational functions, when you have the degree on top equal to the degree on bottom, you just look at their leading coefficients and divide them, and that's where it's going to go. And you can see that on the graph. As you go all the way to the left, it goes to height 3. To see what happens on the right, remember we had to change the window. So if you change this to like negative 50 to 50, you'll see on the right that it'll do a similar thing. So right here, it's going to start heading towards height 3. You know, it does look like it goes to 0, but remember, we're just zoomed out so far, it's hard to see height 3 because we're going to 50 to negative 50. But this one's coming down towards height 3 on the right also. So our horizontal asymptote, instead of x equals, that's a vertical asymptote, we get y equals 3. And then finally, for the graph, I mean, simply sketch the graph using this information that we found. So here's my y-axis, here's my x-axis. We found vertical asymptotes at negative 3. So let's label this vertical asymptote, x equal negative 3. And then positive 8. And we don't want to draw this to scale because we want to get the overall feeling. So even though this is what the graph looks like, you don't want to draw it to scale. Otherwise, you lose what it sort of looks like. We do have a X and Y intercept at 0, 0. And you just kind of want to sketch it. So it looks like it comes up here and then turns around and then comes back down over there. There's the vertical asymptote. On the other side, you can see on the graph, it sort of comes up here, but oh, we got to put in that horizontal asymptote. So let's put one more asymptote in here, but it's a horizontal asymptote, and that's at height 3. So that's y equals 3. Right, that way we can draw the rest of the graph. So here is a horizontal asymptote, so it kind of comes up towards the vertical, like that. And then over here, it starts up here and then comes down like that. You can see this from the sort of graph, so you get an overall feel for what's kind of happening. And that's it. Okay, so now let's redo this with the next function. All right, so the next function was what? The next function was g of x equal to 2/3 x. All right, so g of x equal to 2/3 x minus 7. And so now the domain D, there's nothing that limits our domain here because you're not dividing, so it's everything. And then if you graph the line on your calculator, you'll see it's not a horizontal or vertical line, of course. So it's also going to be everything, but we might as well graph it. So 2 divided by 3 times x minus 7. Let's just do a standard window, so -10 to -10. So there it is down there. And so the range is also everything. All right, so then we want to find the x-intercepts and the y-intercepts. So x-intercept versus the y-intercept. Remember, I don't memorize, what I'm actually doing. I just draw a picture, and the picture tells me how to do this, right? So you have x and y, and then for x-intercepts, you just say, okay, well, that's where you cross the x-axis. All right, so what's that idea? I don't know how far over I go, but the output is 0. So I take the output, which is on the left here, this stuff here, and I put a 0 there and set it equal to the right. So 2/3 x minus 7. To solve this, you add 7 to both sides, and you get 7 equal to 2/3x. You multiply everything by 3 to clear denominators, and you get 21 on the left and 2x on the right, and then divide out by 2, and so 21/2 is equal to x. So the input, that question mark, is 21/2, so 21/2, comma 0. That's the x-intercept. You can look at this on the graph and see that it's going to happen over here. Right, so right over there, it's a little bit bigger than 10, which you can see, yes, 21/2 is a little bit bigger than 10. So for the y-intercept, real quick, the y-intercept, of course, happens right there. There are a couple ways to do this. You can plug in 0, like we did before, or you can just realize that -7 is the y-intercept. So the y-intercept here is that b value, which is -7. And of course, it's a point, so the input is 0, the output is -7. And so that's the y-intercept. So we can actually use our understanding of linear functions, that being the y-intercept, to find the y-intercept for this. Okay, so we have the x-intercept, the y-intercept. Vertical asymptotes are real easy. There are none. And horizontal asymptotes, just as easy. There are none. And then we can graph this thing. So to graph it, we simply draw a y-axis. We know that it goes through -7. And we know that it also goes through 21/2. And we simply connect those dots in a linear fashion. So you can just do it just like that. Label those 2 points, and you're good to go. And then finally, let's do this last one here. So the last one we want to do is h of x equal to x squared minus 10x plus 9. All right, so suppose I want to find the domain of this. Again, you can graph it if you're uncomfortable, but there are no denominators, no roots, and no ln's, so the domain is going to be everything. But it's always good to have a graph going, I think. So here, let's get this graph going. So y equals x squared minus 10x, and then plus 9. And we'll make our window the standard. So number 6 is the standard, -10 to 10. See if we can see anything. Oh, so it goes down, it comes up. You'll notice that it goes way down. So maybe I'll just make my window a little bit, the y min a little bit, bigger negative. So maybe like -20, just so I can see it come down and come back up. There it is. All right, so I already know what the graph's kind of it's going to look like. So I can kind of figure out, what the range is. All right, so for the range, it's going to be equal to, it's going to start at some low value, which is right down here. So I could use a calculator and use the minimum button. Or I could do something else, which I'm going to use something else here to practice completing a square. But then it goes up to infinity. Right? So you can see that, oh, it hits this output low value, and then it goes all the way up to infinity. Now, that low value is actually at the vertex. Let's find the vertex of this quadratic function. All right, so remember, to find the vertex, we're going to complete the square, and in the end, we'll have it written as a times x minus h quantity squared plus k squared. So let's just do this for fun. Again, you could use the minimum button also. So x squared minus 10x, and then the middle term is negative 10. We'll take half of it, which is negative 5, and square it. So we'll add 25, and we'll take away 25. Then we have plus 9. All right, so remember, we just add. Let's write this down so you don't forget. Add half the middle term squared. And we'll do this later on in the review too. Okay, so now what you get, right, this piece right here is actually can be written as a perfect square. So this is equal to x minus 5 quantity squared, and then minus 25 plus 9 is a minus 16. So there's the vertex form of this parabola, this quadratic function. And so you can read off h. H is going to be equal to 5, and k is going to be equal to, and it's plus k, so it's negative 16. So remember the form, which is given to you, is this right here. Let's put it right here, this right here. And so h is 5, and k, ooh, did I write k squared? I shouldn't put k squared. That's just k. Sorry. That's just k right there. And so then plus k, and of course it's minus 16, so k is negative 16. So we have a vertex at 5, comma negative 16, which is nice because it does correspond with our graph right here. So yeah, that looks like 5, negative 16. I'll take that. So that lower height is negative 16. And so right here, we'll put negative 16 for our range. All right, so X-intercepts and Y-intercepts. So let's do that. So remember, for X-intercepts, again, if you forget, you just draw this little XY axis and you ask yourself, what is an X-intercept? That's where you intercept the x-axis. So I don't know how far over I go, but I know the output is 0. So we're going to set this equal to 0. 0 equal to x squared minus 10x plus 9. So this is a quadratic equation. Lots of ways to solve it. You can factor, quadratic formula, complete the square. Let's factor, because it looks like I should be able to factor this. So it's x plus or minus something, x plus or minus something. There's a 9 there, so I could do 3 and 3, but that can't give me 10. If you add or subtract 3's, you can't get 10. But 9 and 1 will work. So if you put a 9 here and a 1 here and make this negative, negative, and that's not a point. Let's get rid of that. I hit that on accident. So put a minus here. That'll work. Okay, so minus 9x minus x is minus 10x. And so then you're going to get minus x minus 9 equal to 0, or x minus 1 equal to 0. If you add 9 to both sides, it tells us x is equal to 9, or x is equal to 1. So we have two x-intercepts, 9 and 0, and 1 and 0. And you can see these on the picture. Yes, there are two x-intercepts, one here and here. So you could have also found them with your calculator by using this 0 button right there. That would also find these things for us. All right, then finally a y-intercept. Let's go over here. And now we're doing so many of these. This is, you set it equal to 0. This you plug in 0. So it's basically saying, what's h of 0? So h of 0 would be equal basically to 0 squared minus 10 times 0 plus 9, which is just equal to 9. Right? So we're just plugging in 0 and you get out 9. So the y-intercept happens, you plug in 0, you get out 9. And again, you can see that right on your graph, right here, that's where it's crossing. So up here at height 9. All right, so x-intercepts and y-intercepts are done. Horizontal asymptotes and vertical asymptotes are very simple because there are none. So for horizontal asymptotes and vertical asymptotes, I did these out of order, but it doesn't really matter, right? So these are none and none. Right, so on this, the graph goes, you can see on the graph that it continues to go up to infinity on the right, continues to go up to infinity on the left, so it doesn't approach anything. And there are no vertical asymptotes. It's defined everywhere, so it doesn't blow up or blow down. And then for the graph, let's just do the graph right here. And we can be pretty specific on this graph because we found lots of things. We found the vertex to be at 5, negative 16. And again, we're not drawing a scale. And then we saw it kind of goes down like this, turns around like this, and goes back up. And we can even label a lot of these points, right? So let's just label some of these points here. So like this was height 9. That was the Y-intercept. And these were the two X-intercepts. And one was at 1, and the other was at 9. Right, so it's definitely not drawn to scale because this is height 9 and this is length 9. But you can see the ideas, right, where these points sort of correspond on the graph, which is important. It's important to be able to look at the picture and look at the sort of words here in some sense and understand how they're connected. I guess they're numbers, but it's a reading thing, you know. All right, so that completes number 2. Let's go on to number 3. So on number 3, what we want to use is slope point form. So remember, slope point form is y minus y sub 1 equal to m times x minus x sub 1. To find the equation of a line containing these 2 points, 4, 3, and 12, 5. So whenever I do a problem like this, I always like to plot the points. That way, if I make a silly mistake, I can catch it. So 4, 3, let's put that right here. And then 12, 5, let's put that over here. Again, it does not need to be drawn perfectly or to scale. We just want the idea down here. And the idea is that you can see that this line is going up, so the slope better be positive. So if we want to find the slope, m, which is the rise over the run, right, or the change in the output, the change in the y, or the change in the x, what we're going to do is we're going to take these y values and subtract them, so 5 minus 3, divided by, so it's always the output over the input, divided by, if you start with 5 on top, you start with 12 on bottom, so 12 minus 4 on bottom. That way the signs don't get mixed up. And so you have a 2 on top and an 8 on the bottom, so you get back 1/4 for the slope. So now that I have the slope, I need a point. I have lots of points. I'm going to choose this point to plug in because it's smaller. So I have y minus, and then y sub 1, which is my 3, is equal to 1/4, x minus, and I need x sub 1, which is going to be my 4. And I simply solve this for y, so y minus 3 is equal to 1/4 x, minus, now 1/4 times 4 is a 1, and then I'm going to add 3 to both sides, and I get y equal to 1/4 x plus 2. Now that should be the right answer. To check my work, I'll use the second point that I didn't use in the formula. So I'll plug in 12 at 1/4 times 12 plus 2. And that's equal to, so 4 goes into 12 3 times, so 3 plus 2, which equals 5. And yes, that's a 5, so it checks. So I'm positive that this is the correct answer. So that's how you find the equation of a line using slope point form. Now, there is a second way to do this using y equals mx plus b. Right, but if you did it this way, using this formula, the problem would be wrong. You get some partial credit, but you would lose points for not using the slope point form. So make sure you use the right formula and you're solving this problem if it explicitly tells you how to do it. All right, so number 4. Now we move on to a quadratic function, and we want to find its vertex by completing the square, and then just graph it. We can actually graph it in the beginning if we want to, just to get an idea of what it's going to look like. So let's clear this out. And we have x raised to the 2 plus 6x plus 11. And then we can just do a standard window, so zoom and hit number 6 for -10, -10. You kind of see it. Oh, and that's great. So it comes down, it goes back up. So I already see what it looks like. And in fact, if I really want to, I could probably just draw this graph kind of doing this. And what I need to do is I need to find that vertex down there. So I need to find that vertex, and I'm going to do that by completing the square. So let's copy down the formula. So they give us this x squared plus 6x plus 11. And remember, the idea is that I want to rewrite this as some number times x minus some other number squared, all quantity squared, and then plus a k, plus some other number. And the way we're going to do that is we're simply going to add half the middle term squared. So the middle term is 6. We're going to take half of it and square it. So half of 6 is 3. If you square it, you get 9. And take away right next to it. And if you do that, if you add half the middle term squared, this will have a nice property. That can be rewritten as a perfect square. So it can be rewritten in this case as x, and it's plus, because there's a plus there, 3 quantity squared. And then plus, you have minus 9 plus 11, which is plus 2. And so that has the right form now. And I can read off my h. My h is not going to be 3. It's actually going to be negative 3 because it's x minus h. So this is x minus a negative 3. And then my k is 2. So my vertex is equal to negative 3 comma 2. And so I can basically just label this negative 3 comma 2. It's also nice to label a second point, and that's usually one of the intercepts if there are intercepts. So this has a y-intercept. And remember, the y-intercept happens when you plug in 0. So when you plug in 0, that's 0 and that's 0. So that's just the height of 11. So it's always nice to have 2 points when you're graphing a quadratic function. Perfect. Let's move on to number 5. So number 5 says, find the zeros of the function in 2 different ways. First by completing the square, and then using the quadratic formula. And we're going to mix this up. Let's use the quadratic formula first. So the quadratic formula was given to us on the front of the page of this review. And so it says what? It says if you have a function, basically, not a function, but an equation, ax squared plus bx plus c equal to 0, then you can find the roots x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's basically what we have here, because it says find the zeros. So what we want to do is we want to set this thing 2x squared minus 6x minus 5 equal to 0, right? To find the zeros of the function. All right, so we can just identify our a is equal to 2, our b is equal to negative 6, and our c is equal to negative 5. And so x should be equal to negative b, so that's positive 6, plus or minus the square root of negative 6 squared, so that's 36, minus 4 times a, so 4 times 2, times a negative 5, all divided by 2 times a, so 2 times 2, which equals what? So you have 6 plus or minus the square root of 36 plus, it's plus because it's negative, and here you have what? You have 5 times 4, which is 20, times 2, which is 40, and that's all over 4. And we keep on going here, 6 plus or minus the square root of, what's this, 76? Yeah, 76, all divided by 4. And you have to watch out here to make sure that there are no perfect squares inside 76, and I bet 4 goes into that. So what we want to do is realize that this is the same as 6 plus or minus the square root of 4 times what? So 4 will go into this once, and then 9 times, right? So 19. So 4 times 19, which is 40 and 36, yeah, that's 76, all over 4. And so that's nice because the square root of 4 is 2. So we can write this as being equal to 6 plus or minus 2 root 19 all over 4. And then we're going to give 2 to each of these. Right? So when you give one of these 2's to 6, you get 3. So you get 3 plus or minus, and this also gets a 2, so over root 19 all over 2. And that should be my final answer. So 3 plus or minus the square root of 19 all divided by 2. You can check this answer, right? So let me show you how you can check this answer A couple ways to do it, but probably the easiest way is just to plug this number in. So let's do like 3 plus second square root of 19. Kick it out. In parentheses divided by 2. So that's one of the roots, and it's that number there. So what we're going to do is we're going to take 2 and then second answer squared, and then we're going to take away 6 times that answer. So 6 times, so 6 second answer, and then we'll take away 5. If we get back 0, we did it right. If not, we made a mistake, and we did it okay. You can even be fancy about this and check the other one pretty simply by hitting second enter and second enter. And then instead of a plus there, we go back and we change it to a minus. And we hit enter. And so there's the second root. And you can check it really simply by hitting second enter. Second enter. So there it is. 2. Here's your answer squared. Minus 6 times your answer minus 5. Hit enter. And we get out 0. So not only did I solve the problem, but I know I solved it correctly because I checked it with my calculator. Which again, I normally wouldn't do to the end of an exam because it does take some time. All right, so now let's take this equation. Let's rewrite it, because now we want to use completing the square. To solve it. We should get the same answer. And so let's rewrite it. So 2x squared minus 6x minus 5 equal to 0. And now the problem is we can't complete the square as it's given because there's a 2 right here. So we have to get rid of the 2. So the way we get rid of the 2 is we factor out the 2. So it's 2 times the quantity x squared minus 3x in parentheses. So this times this is that, this times this is that. And then minus 5 outside the parentheses equal to 0. So we haven't changed the expression or the equation of all. We just made it look different. That way we can apply this technique of completing the square where we add half the middle term squared. Now, this one's a little bit difficult because when I factored out the 2, this was odd. So somebody asked me about this in class. I'm not going to change it. If we had this on the exam, this would be an even number, so half of it would be nice. But I think it's nice to see, how these things work when they're not so nice, because the same techniques work. So half the middle term squared. So what's half of 3? Well, half of 3 is 3 halves, and then you're going to square it. So you square this top and bottom. So we're going to add 9 over 4, and we're going to subtract 9 over 4. In parentheses, minus 5 equal to 0. And again, this will have this nice property right here of being able to write this as what? As 2 times x, and it's going to be minus, because there's a minus sign there, minus 3 over 2, quantity squared, minus 9/4, and then all minus 5 and equal to 0. All right, so this is a perfect square right here. And then we'll multiply through by 2, so we get 2 times x minus 3 over 2, quantity squared, minus, if you multiply 2 times 9/4, you get 9 halves. All right, so it's this times this, and this times that. So the 2's cancel out top and bottom. And then minus 5 equal to 0. We could even find a common denominator right here. So what do we have now? We'll have 2 times x minus 3 over 2, quantity squared, minus 9 halves. And remember, this is 5 over 1, so we'll multiply top and bottom by 2. So minus 10 over 2 equal to 0. And we just keep on going at 2 times x minus 3 halves. That's a terrible 3 halves. So let's change that. So x minus 3 halves, quantity squared, minus, so minus 9 minus 10 is minus 19 all over 2 equal to 0. And we keep on going here, so we'll add 9 halves to both sides. So 2 times x minus 3 halves, quantity squared, equals 19 over half, 19 over 2. So we add 19 over 2 to both sides. And we divide everything by 2. So we divide this by 2, divide this by 2. Change colors here. And so on the left, you're going to get x minus 3 over 2, quantity squared, equal to, now remember when you divide by 2, it's like multiplying by 1/2. So you multiply by the reciprocal, so you get 19 over 4. And then to undo the square, We're going to take the square root of both sides, so you get x minus 3/2 equal to plus or minus the square root of 19 over 4. The square root goes through division, so this is x minus 3/2 is equal to plus or minus the square root of 19 divided by the square root of 4, which is 2. And then we're going to add 3/2 to both sides, so you get x equal to 3/2 plus or minus the square root of 19, all divided by 2, which these are exactly the same problem, or same answer. Right. So that's completing the square. This one's really tough, I think. So much harder than I'd have on an exam, but if you could do this one, you could do any of them. I think that answers our question. So here we wanted to solve this. Yep, solve this in 2 different ways, which we did. Let's look at the next problem, classifying the polynomial. So here's our polynomial. And we want to classify it as being a linear, quadratic, cubic, or quartic. Now notice the degree here is 0, 1, 3, and 2. So they didn't write it in order. So maybe we should just rewrite this quickly from largest degree to the smallest degree for each term. So you'd have negative 2x cubed plus 7x squared minus x plus 5, which is the same thing, but now at least it's degree 3, degree 2, degree 1, and degree 0. So it's easy to see that this is actually a cubic polynomial. It has degree 3. The leading coefficient, of course, the leading coefficient is negative 2. The leading term is the term with the highest degree here, so it's this term right here, so that's negative 2x cubed. And then the degree of the polynomial is obviously 3. And then what choice represents the end behavior of this polynomial? So, it's basically saying, hey, as x goes to infinity, what does f of x do? And as x goes all the way to the left, so as x goes to negative infinity, what does f of x do? There are 2 ways to do this. You can plug in really big numbers here, and you'll see that if you plug in a big number like 100, you get a big number out. When we multiply by negative 2, you get a big negative number. So this will be negative infinity. Versus if you plug in negative infinity, or if you plug in a really big negative number like negative 100, this will be negative because you're cubing it, and then times the negative will make it positive. Right? So on the left, on the right, it's going to go down, and on the left, it's going to go up. So pretty sure it's going to be D. If you want to make sure and check it, you can always use your calculator. So we can graph this thing, y equals, and let's plug it in how they gave it to us. So 5 minus x. Oops. So 5 minus x minus 2 x raised to the 3, and then plus 7x raised to the 2. And we can just do a standard window. So zoom standard. So Z standard. So it looks like this and down. So you kind of see it goes down over here, and then it's going to go up over there. If you want a better one, we can zoom fit it, and you get a better picture of the overall activity. You can't see what's happening in here because it's zoomed out too far, but you see it goes down and up over here. So yep, that's exactly what I thought it would do. So that's working with polynomials. And then number 7, we want to talk a little bit about the zeros or the roots and their multiplicities. Okay, so on this one, it says use a graph of the polynomial of f of x. So here's the graph here. And to determine the zeros, so there's obviously 2 zeros. There's a 0 here at 0, and there's a 0 there at 3. And whether the multiplicities of each 0 is even or odd. So, and a possible formula, right, based on this information. So the zeros are easy to find. It's x equals 0 and x equals 3. The multiplicities, right, so the multiplicity for each 0, so for x equals 0, I don't know the actual number, but since it turns around, right, it turns around there, because it turns around, this implies that the multiplicity has to be even. Whereas at x equals 3, it crosses the x-axis. So because it crosses this implies that the multiplicity must be odd. And then finally, for a formula, f of x, well, what you know is it has zeros at 0 and 3, so it has to have some sort of form of, let's erase this. So at x equals 0, it's like x minus 0, so it's just x to some power, and then times x minus 3 to some power, right? These are question marks. We don't know what the powers are yet, but we know that on 0 it has to be even. So for even, the smallest even would be probably number 2. And for odd, all right, so what's the smallest odd number that's still positive? So that would probably be 1. So let's make that a 1. And let's check in our calculator, and let's see what happens. So this would be x squared times x minus 3. And so on the calculator, we clear this out, and we just take x raised to the 2, left parenthesis, x minus, so to the 2, and then left parenthesis, x minus 3. We'll do a standard, well, we'll make their window look just like theirs, right? So -2 to 4. So -2, enter, 4, enter. Then go down to y min and make it -10, enter, and 2. Enter and hit graph. If it looks just like theirs, we're done. And so it looks pretty close. You see that? So it goes up, but it comes down. The only difference is, if you notice, theirs goes down to -8, where ours goes down, it looks like to -4. So how can we make that go down further? How can we make -4 turn to -8? Well, you can just multiply this whole thing by the number 2. So it basically looks the same. You just have to put a 2 there. And if you put a 2 there, it's going to make this -4, right? It's like a transformation. It keeps these stay here, right? When you multiply the heights by 2, this has height 0, so it's going to stay there. That's going to stay there. But this is going to stretch it down by a factor of 2. So let's do that. Let's put a 2 in there. So second insert, 2. And then hit graph again, and you'll see you get exactly this graph over here. And if you didn't see that, it's not a big deal. But if you see it, that's great. All right, so this is my formula right here. F of x equal to 2x squared times x minus 3. This is probably a little bit too hard for an exam, but it's a great multiple choice problem, right? So pick which one it is, A, B, C, D, or E. All right, let's move on. So number 8. Oh, this is a good one. So just use the graph here to answer the following questions. And so we have this arrow notation. These sort of fill in the blanks. I like these here. So as x goes to 4 from the left, so here's 4. And we're going from the left. Oh, and I want to change this. This should be a 5. This should be a 5. So as I want to go towards this vertical asymptote. So as you go to 5 from the left, so you're on this side, you see that the function goes down. And so over here you write -infinity. Versus if you come in from the right of 5, so here's 5 right here, coming from the right now, you see on the function, you trace the function above it and it goes up. So it goes to positive infinity. Versus, right, so now we're going to change directions here. We're going to look at the input. So as the inputs go to -infinity, so as the inputs go all the way to the left, look at the graph, it also goes all the way to the left, but it approaches this height of 1. So as you go all the way left, the function approaches height 1, versus now we go to positive infinity, so we look all the way to the right, and we trace the function, and it goes also to height positive 1. So what this tells us basically is this right here gives us a way to define, in some sense, vertical asymptotes and horizontal asymptotes. So this tells us that there's a vertical asymptote at x equal 5. There's also one over here at x equal -1, which we didn't do up here, but we could if we wanted to. And then there's a horizontal asymptote, of course, not at x equals, but at y equals height 1. Okay. All right, let's go to some of these word problems now. So 9, 10, 11, and 12 are the sort of modeling type problems. So you have linear models, quadratic models. We even have polynomial models, but we didn't do those because we didn't have time because of the closure of building A. But then we did rational models, right? But remember, the polynomial models, quadratic models are polynomial models, and so are linear models for that matter. All right, so let's take a look at this one here. And so it says the formula, and gives us the formula, I equal to 1/4 t plus 21, models the percentage of households with interfaith marriages, I, t years after 1985. N equal to 1/3 t plus 4, models the percentage of marriages in which a person of faith is married to a person with no religion. N, which is t years after 1985. In what year will these percentages be the same? So these are interfaith marriages. This percentage of interfaith is a percentage of basically faith and no faith marriages. In what year will these percentages be the same? So that's sort of our picture. All right, so you have one formula, 1/4 t plus 21, and then you have, those are interfaith, and then you have one with basically no faith, and one of faith, and you want to find percentages same. And so what do you do with these two formulas if you want to find same? Well, you simply set them equal to each other. So 1/4 t plus 21 equal to 1/3 t plus 4. And this will find the, I should put the year, that's important, the year. I want to find the year that this happens. And there are two ways to solve this equation. You can use technology. You can graph the left, graph the right, and find where they intersect, or you can solve it by hand. I think I'm just going to solve it by hand because it's a good problem of basically finding common denominators, or I shouldn't say common denominators, I mean clearing the denominator, right? So there's a 4 and 3 here, so we'll multiply everything by 12. That'll clear the 4, and that'll clear the 3. So 12 times this. So the 4's cancel, and you get 3t, plus 12 times that, which is 10 times that, which is 210, plus 12 plus 12. So 210 plus 24 is 234, and equal to then 12 times this, so 3 over 12 is 4, so you get 4t here, plus 4 times 12, which is 40 and 8, so you get 48. And so I want to solve this for t, so what do you want to do? Let's take 48 away from both sides. Let's move that over first. And so what do we get here? We're going to get 3t equal to, oops, I already messed that up. So we get 3t on this side, and then plus, so 234 minus 48. So you're going to take off 34, which leaves us with 14 left. And so we're going to get 186 here, equal to 4t. And then we're going to subtract 3t on both sides. So minus 3t, minus 3t. And so we're going to get 186 equal to t, which seems like a lot of years since 1985. Let's check this real fast because I feel like that might be off. Maybe I made a mistake. So let's check. So if I made an algebra mistake, right, which is easy to do, and I feel like it's a lot of years, but let's check it. So we have 1 divided by 4. And then we have x plus 21. We're going to graph the left. And then we'll also graph the right. So 1 over 3 x plus 4. And then we're going to make our window. Now, my window is going to start at 0 because it's t years after 1985. And I'm going to go all the way up to 200 because I found that t was 186. So then let's zoom fit it and see if that's actually right. So there's the first graph. That's 1/4 t plus 21. Yeah, it looks like it might be right, huh? So maybe. All right, so let's see if we can find where they cross. So second trace, and then intersect, and then first curve 0, enter, oops. So second trace, intersect, so number 5. First curve, enter, second curve, enter, give it a guess, enter. And let's see what it finds. Oh, no sign change, which means it doesn't cross on the screen. So did I enter this in right? So 1/4 x, plus 21, 1/3 x plus. So this one says that it's actually even bigger than that. So let's go up to 250 and zoom fit it. So basically my math was even more wrong than I thought. So second trace, and then we'll hit intersect. 1, 2, 3, and it'll find it. So this found 204. All right, so here this found that 204. So we're going to go back and find my mistake. It's probably my basic arithmetic, which is always pretty bad. All right, so 204. Let's find my mistake. So it could happen in a number of places. You know, when I did this 21, I didn't really multiply it out. I multiplied out in my head, which I probably did wrong. So I got 252. Oh, I was way off. All right. Oh, it's 21 and I did 12. Right. My brain, brains get things backwards. Okay, so that was my big mistake. This should have been 252. So let's correct it. So let's erase this right here. This should be 252, which is going to change this, which will change that. And so let's put 252 right here. So 252. We'll take off 48. So when we take off 48, let's just go back to our calculator so we don't make any more silly mistakes. And I get 204. So this right here will be 204. And so the right answer, of course, when you subtract 3 on both sides, is 204 equal to t. So that's 204 years after 1985. So to find the year, I'll add 1985 to it. So we'll do 19, so plus 1985. And we'll get in 2,189. So 2,189. So that's my answer for that one. So this is a good example where I got an answer where I didn't know if I necessarily believed it or not, so it's so far away. But I wanted to find, I used my calculator to check my work, and I obviously made a silly mistake here. It's easy to make mistakes on things like this, so be careful. And if you did make a mistake, if you show your work, like if you would have done this, I would have seen what you've done. I'm like, well, why did they do that? Oh, it's just a multiplication error. And if it's real clear, sometimes I won't take off anything because mistakes are easy to make when you're doing basic arithmetic, especially with the time constraints on this class. You can test your work, which is not part of your solution. So if I had time, I'd come back and I'd test my work by plugging 204 in for t here and here. I better get the same answer out. So if you take 1/4 times 204 and you add 21, you're going to get a number out. Versus if you take 1/3 times 204 plus 4, you'll get another number out. And we can do these on our calculator. So 1 divided by 4 times 204 plus 21. And that's equal to 72. So right here, you could put 72. Which means this better be 72, otherwise I did this problem wrong. So 1 divided by 3 times 204 plus 4, and I do get out 72, so I know I did it right. And this is something I would do at the end of my exam if I had time, because again, if you make a silly arithmetic error and I can see your work, it's not a big deal. And you can also use technology to solve this, because again, it didn't say how to solve it. All right, let's move on to the next problem. And so now we're going to work with a quadratic function. And so what we have here, it says the height of a ball, h in feet, thrown into the air can be modeled by this function, where x is the ball's horizontal distance in feet from where it was thrown. We want to find the maximum height of the ball and how far does the ball go horizontally before it hits the ground. So let's just draw a graph. So on this one, the maximum happens at the highest point on the graph. So what I'm going to do is I'm just going to draw a graph of this thing. I don't really need to do picture equation solve on it, nor did I need to do it really in the last one because I kind of knew exactly what to do. The same thing with this one. It's kind of like, well, just draw the graph and use the graph to figure out how to solve the problem. So here you have negative 0.2 x raised to the 2, and then plus 1.4x, and then plus 8. And we'll make our window go from 0, and let's try 100 feet first to see what that does. And then do zoom fit. and the ball should go up and come down. It looks like I went way too far to the right, so it's way up here, so I need to change this window. Let's go to 10 feet. Ooh, where'd you go? 10 feet. And let's zoom fit it. So let's go to 10 feet. Zoom fit. There it goes. That's much better. So it comes up, comes down, right over there. I might even want to go to 15 feet because I saw it hit the ground there, and we'll go a little bit further. All right, so it goes up, comes down. Now, I don't care about the negative stuff. It hits the ground right here, so it doesn't go through the ground. So it hits the ground right there, but you get a good idea of kind of what's going on. So when I answer this question, I probably would put a graph up where it comes up and goes down and went from 0 to 15. So for part A, which says find the maximum height, I'm looking for the maximum. So again, you can do this by hand by completing the square and writing a vertex form, but I would probably use my technology. So I hit second trace, and then to find the maximum, I hit maximum. So I hit number 4. And then it's going to say left bound, so I'm going to do 0 because that's on the left. And then 15, because 15 is certainly here on the right. And then hit enter for a guess. And it's going to pop up here, and it says x is 3.5 and y is 10.45. So now you have to figure out which one they want. Well, they want the maximum height, which is not the input, but the output. So right here, I might write something like, max, because I find the maximum. And so the maximum height is equal to this 10.45 feet. That's the maximum height. And then in part B, it says how far does the ball go horizontally before it hits the ground. All right, so on this one, they're looking for where it hits the ground right here. And so that's where you have to find the 0. And so on my calculator, right, or you could also write down the formula. You're taking the formula here, negative 2.2x squared plus 1.4x plus 8, and setting it equal to 0 and solving for x. And you're going to solve this for x. So I would just use my calculator. And it has a 0 button, so I'd hit second trace, right, to pull the calculate menu. 0 is number 2, so hit number 2. And then left bound and right bound, well, there are all kinds of ways to do this. You could just use these little arrow buttons if you want, which takes forever on my calculator. So I'm just going to hit, so left bound is like, well, 0 is definitely to the left, so I'm going to hit 0. And then 15 is definitely to the right, so I'm going to hit that. Then I'm going to hit enter, and it's going to pop right to it. All right, so now this has negative 1. Now e to the negative 12 is actually 10 to the negative 12, which means move that decimal place over 12 points to the left. So that's basically 0. And now this one says how far does the ball go. So I'm going to say x is approximately, let's do 10.7 feet. We'll round. So x is approximately 10.7 feet. I'm just going to round it, I think. That's probably the best way to do it. All right, you can check your work by simply plugging in 10.7 into the formula. So let's see what happens when we do that. So if I was going to come back and I was going to check my work, what I would do is I'd hit negative 0.2 times 10.7 squared. And then I would add 1.4 times 10.7. And then plus 8. And I should get a number close to 0, which is 0.082. So it's close enough. All right. There were some decimal places that I rounded off, but it's close enough to 0 to make it work. What's next? Okay, so next, let's look at number 11. Oh my goodness, so number 11 and 12. All right, so 11, now these are picture equation solving test problems for sure. And there's no way getting around these things. Okay, so you're going to do a picture. And so a farmer decides to enclose a rectangular garden with 600 feet of fence using the side of a barn as one side of the garden. Find the maximum area of the garden. So you have a rectangular fence, and you have a barn on one side. So over here, I have a barn. It does not matter which side you put the barn on, but you have to put it on one side. So you have side X, and side Y. You're going to need fences on this side, but not on the other, right? So remember, there's a barn right here, so you don't need any fence right there. You have 600 feet of fence. And of course, you want to find the max area of the garden. So find max area. So that's my picture. My equation is really easy to find because I want to maximize the area. So you look for an area equation, or formula for the area. So it's length times width. Right, so you're looking for this area. So you take length times width, which is just x times y. You're in this funny situation where you don't know that you can't graph it because you have x and y. So you need to figure out one of these. So that's where this 600 feet comes in. So that's 600 feet of fence. So the 600 feet of fence, that represents, if you add up all the sides that you have fence on, you should get back 600. So here you're going to have x and x. So that's going to be equal to 2x. And then plus a y. And so we're going to solve this for y. And if we do that, we can plug into the other formula and eliminate y. So you get 600 minus 2x equal to y. We come over here, a is equal to x. And then wherever you see y, you're going to put this 600 minus 2x. And you have to be a little bit careful because you can't just write 600 minus 2x. If you wrote that, then you would have x times 600, but not x times the 2x. So you need to put parentheses around this. And that's perfect. That is a quadratic formula, or quadratic function, because x times x is x squared. You don't need to multiply through by x if you don't want to, because we're going to use our technology to solve this. And so I need to open this up again. I guess I lost it. So let's open up the calculator. And you can hit y equals on your calculator as soon as you have it going. And then you're going to plug in that formula. So we'll hit y equals, and we'll clear this off. We have x, left parenthesis, 600 minus 2x, in parenthesis. Then we'll make our window. Now our window, we're going to start at 0, and we have 600 feet of fence. So what I'm going to do is I'm going to go to 300. The reason I'm choosing 300 is if this is 300, then this is 300, so you have 600 total. So it's as big as x can be, actually. And then I'll hit zoom. I'll hit 0 for zoom fit, and it gives me a great looking graph. So I'm going to copy that down. So I went here, 0 to 300. It came up. It came back down. And I'm looking for that maximum. Right, so this is the graph. If the input is the length of the fence here, it gives you the area as the output. So I'm going to use the max button. So on my calculator, I'm going to hit second trace. I'm going to go look for that maximum. So I'm going to hit number 4. Left bound is 0. Enter. 300, because definitely 300 is definitely to the right. Enter. Guess. Just hit enter. And it's going to pull it up. So let's say x is 150, y is 45,000. Now x is this x, but remember this y and this y are not the same, so this is the output, which is my maximum area. So that's what I really want. So I'm just going to write down the max area is equal to 45,000 feet squared. You can write down the 150, but you need to put the answer in a box so I know you know what you're actually telling me. So it's 45,000 feet squared. It does not ask for y. If it did ask for y, you can find it by plugging that x value, 150, right into there. Yep. So x is 150. You plug it right in there, and you'll get y equal to 300. But you don't need it. All you need is a 45,000 feet squared. And let's look at the last problem. So this was a modeling with a quadratic function. This will be modeling with a rational function. And here we'll stop with this. So you have a picture. So here we have a landscape architect plans to enclose 6,750 square foot rectangular region in a botanical garden. So you have a rectangular region. It has an area. I know it's an area because it's square foot. All right, so square feet basically. So 6,750 feet squared. Okay, that's this area right there. And she will use shrubs costing $15 per foot along 3 of the sides. So let's add some color. We have some shrubs here on 3 sides. Any 3 sides you want, you can just pick them, but you have to pick 3 sides. So I'm going to put them on these 3 sides. And so my shrubs are $15 per foot. Versus I'm going to have a fence on the 4 side. So, and fencing costing $10 per foot along the 4 sides. So there's a fence right here. So then my fence is $10 per foot. And then what do we want to find? All right, so $10 per foot. And then we want to find the min cost. So find min cost. So my equation, it's not an area equation, it's not even a perimeter equation, it is a cost equation, C. And it depends upon the lengths of these sides. So let's label this X, this Y, and of course then this is X and this is Y. And to find this cost equation, you're going to have to think a little bit, because either you know how to do this or you don't, basically. And if you don't, you have to kind of come up with the equation. You say, okay, well, the shrubs are $15 per foot, so you have X feet here. If you can't abstract this, what you do is you kind of actualize the problem. Like pretend like you had 1 foot. How much would 1 foot cost? Well, it would cost $15. If you have 2 feet, it would be $30. So 2 times 15. If it was 3 feet, it would be 45. 3 times 15. If it's X feet, it's basically X times 15, or you could write that as 15X. So that's the cost of this one side if this is X feet long. And then once you see that, it's really easy. This side is Y, so it's 15Y. And this side is X again, so it's 15X. And then finally, this side's a little bit different because the cost is different. Instead of $15 per foot, it's $10 per foot, so it's plus 10Y. And so my cost function is actually 15x, 15x, so 30x's plus 15 and 10 is 25y's. And now we're in the same situation we were in last time. We have x and y, so we can't graph it. We need to get rid of one of these numbers. And so that's where the 6,750 comes into play. Now that's the area, which is length times width, so it's x times y. And we solve this for y by dividing both sides by x. Since we're multiplying by x, to move it over, we divide. And we get 6,750 divided by x equal to y. And then we're going to substitute in for y. So here's y. Remember what it's equal to. So again, I always think of these as sort of like a flashcard. Up front you have y, and then you flip it over, and 6,750 over x is on the back. So this is going to be 30x plus 25 times 6,750, all divided by that 5. That's a 5 there. Okay, it's 50 over x, which is equal to 30x plus, and then I'll need a calculator, so I'm going to do 25 times 6,750, which is equal to 168,750. So let's write that down. 100. Ooh, whoa. Wrong pen. So 168,750, all divided by x. And so this is my c, my cost function. Now this is a rational function because you're dividing by x. So when we solve this, we're simply going to graph it. So take out your calculator and let's graph it. So y equals, clear this, I have 30x plus 168,750 divided by x. And we'll use our window. So x is the length of this side. So what I'm going to do is put in 0 and then go up to, oh, I don't know. So it's a botanical garden, so let's do 100 feet. It's got to be a pretty big garden. And then zoom fit. And now we're looking for a minimum, so it should come down and come back up. Now it came down, but it was hard to see come back up. It may be that my window is too small, so let's just increase this. Let's increase this to 500 feet. And then zoom fit again. There it goes. So it came down, it comes back up, perfect. Let's go here. Came down, it goes back up. All right, something like this. This is 0 to 500. We're looking for the minimum. So we use the minimum button on our calculator. So second trace, go down to number 3, hit enter. 0 was on the left, 500 is on the right. Give it a guess. It should pop right to it. So x is 75, so that means that length is 75. And then be careful, this y and that y are not the same. This is the output, which is our cost. So our minimum cost is $4,500. So our min cost is equal to $4,500. And that's what they want us to find. So they said find min cost. They didn't say find dimensions, but if I did need to find the dimensions, the calculator that gives you x, and to find y, you would just plug right back into this formula here. But that's my answer.